Okay, now that we have gone through the security module, we come to FireNet or firewall networks. So we have talked about, multiple security capabilities within the security section. We've talked about the first one. There are multiple places where you can insert security in the cloud. The first one is the intra-spoke traffic, which means this is the traffic that is within the VPC, but does not actually hit the spoke gateway. And this is best done via our cloud distributed firewall, which we'll discuss in an upcoming module, and is basically about orchestrating security groups and network security groups to lock down your workloads and ensure security within the VPC. There is also the capability which we've discussed in the security module, which is to have a centralized layer 4 firewall at the transit. So if you remember back from our security module discussion, is that every gateway we have has the capabilities of doing layer 3, layer 4 firewalling. And again, if this is sufficient for you, if this is sufficient for your requirement, this could be a great solution. Then finally, which is the topic of this module, which is about having that you want beyond layer 3, layer 4. You want to have a next generation firewall at the transit because you want to do maybe IPS or inspect the traffic at layer 7. Okay, so again, we don't look at these as separate options. We look at them as complementary, and thus you even if you have a next generation firewall, you might still use for example, the firewalls on the spokes, or you can even use you will always need the security within the VPC, because there is certain traffic that even does not that the firewall will not have, the next generation firewall will not have visibility for. Okay, so there are many business and technical requirements that mandate layer 7 inspection. Mostly they are drivers around security, compliance, and audit. Because the cost of an attack nowadays is very high, and CEOs and organizations are doing their best to ensure that they do not get compromised. Thus, layer 3, layer 4 is not sufficient, and thus we require more advanced level inspection with next generation firewalls and IPSs. Okay, there are also some compliance requirements that drive the requirement for next generation firewalls, like PCI DSS or HIPAA, and some other requirements. So there are multiple traffic patterns that require next generation firewall. Again, this is very high level, but just to go through it. There is traffic that goes between VPCs or inter VPCs. VPCs could be VNets, could be VCNs, depending on which cloud, but the concept still holds true. There is the traffic that goes to or from the internet. You want to have ingress, egress protection. And if you have like an on-prem location, a data center that also talks to the cloud resources, you can also have the traffic go through the next generation firewalls. In addition, if you have partner sites or branches. And finally, if you have multiple regions or multiple clouds, you might, you can possibly get the traffic through this firewall network and then send it to its intended destination. So what are some of the challenges of the service insertion in the cloud? I think the problem is the fact that what the firewall vendors have done is they have they have repackaged their solutions. I mean, they have their virtual machines, and they have just repackaged it to run on the different CSPs. And they are completely not concerned on how traffic reaches this appliance. The problem is also on the cloud provider side, configuring routing and via the route tables, via things like gateway load balancers like in AWS or load balancers in Azure, and configuring endpoints, VPC endpoints or interface endpoints. All of this is very, very complex. And there are certain things, for example, in AWS, when you do gateway load balancers, there is Geneve that comes into the picture with overlays. So there is a ton of complexity in order to get the setup to work. And even if you forget, I mean, after you set it up, any disruption, any change within the environment, it's a very hard problem to figure out where it is broken, what changed, because you're probably dealing with multiple route tables. Even in a large setup, it could be 15 to 20 route tables. You need to monitor their changes. You need to look at if is the firewall receiving the traffic, is the firewall up and down, and you need to manage this whole solution together. And the customer is really left between the two, between cloud providers, which really do not provide the simplicity of deployment, in addition to the visibility and troubleshooting tools at your fingertips to figure out what's happening, and between firewall vendors that are only concerned with applying policy once the traffic reaches them. What we're looking at here is a bit of the complexity of deploying PAN firewalls in the cloud. So again, we're not really picking up on Palo Alto by any chance. I think it's one of the best documents that is done. The reason we show the document is to appreciate and understand the level of effort that is required to get a deployment of the Palo Alto firewalls in the cloud, and the same would apply to other vendors. It's not really a Palo Alto problem. I think Palo Alto actually documents it very, very well. So basically, like when we look at AWS, right, after you choose you want to deploy the firewall in public cloud, you have to choose which public cloud. And if you look at an architectural guide that is 84 pages, and then you start looking at the deployment guide, depending on which deployment model you want to go with, you're literally like reading books in order to figure out and to understand the architecture. And then once you decide which architectural pattern you want to follow, then you will need to go and deploy that architectural pattern. If you're using Panorama, there's a third deployment guide that you need to go through. Okay. Again, this shows you the level of effort that is required in order to deploy the firewalls. It doesn't get any easier with other cloud providers. In my opinion, it even gets a bit more, at least from the length of documents. So coming back to some firewall architectural options in the public cloud. So there is the instance level firewalls, which are about security groups and network security groups, which we will cover more in depth with our distributed cloud firewall. There is the CSP provided layer 7. So now what's happening a year or so back, even a bit probably more, AWS now has a firewall. They call it the AWS network firewall. Azure has the Azure firewall, right? So these CSPs are coming up with their own layer 4 to layer 7 firewalls. However, they still, in my opinion, at least based on what I've seen, is they're still a bit behind the next generation firewalls who have been doing it for 10 plus years. The other thing to note is when customers choose to deploy, for example, a Palo Alto or a Checkpoint or a Fortinet, they generally want to follow the same operational model that they do on-prem. So if they're having logging, they want to do that logging. If they have a central management, they want to keep using that, right? Because at the end of the day, you want to keep as much as possible operations consistent. You want to keep everything being operated and troubleshooting to happen in the same manner and process. And this is why we see many customers going and expand their next generation firewall footprint by adding another Checkpoint or another Palo Alto or another Fortinet in the public cloud. Okay, so then there is so what Aviatrix brings in the picture? Aviatrix takes the best of both worlds, meaning that it takes those next generation firewalls, it integrates them at the transit level, and it simplifies and provides a solution that works across all clouds in a repeatable, automatable, and very easy to operate model. This is what FireNet is all about. So let me just get the animation and then, okay. So in a nutshell, what we're doing with FireNet is we are integrating firewalls at the transit layer. Somebody might ask, why the transit? Because the transit is generally the hub. Any east-west traffic that goes between the VPCs or VNets or VCNs has to go through the transit. And thus, it's a very strategic place to insert the next generation firewalls. And what we do with the solution is we're able to do multiple availability zones. We're able to have multiple firewalls in each of these availability zones. We're able to manage everything in terms of route management, even of these firewalls, and end-to-end routing, again, including these next generation firewalls. In a nutshell, we manage the end-to-end life cycle of the solution. We're able to bring up the firewall, meaning from the controller or Copilot, you are able to deploy these firewalls. You are able to configure their network interfaces. You're able to bootstrap these firewalls, meaning so that when these firewalls come up, they come up with an initial configuration, right? And then you can add them to your central management and manage and operate them day to day. But you are able to bring up these firewalls with the IP addresses, with the routing tables, with a very basic policy that even might allow traffic. And then from there on, you can go and make the necessary changes. Okay, and as I said, we're able to spin up the firewall virtual machine, be it a Palo Alto, a Fortinet Checkpoint, or even you can bring your own appliance if you're not using any of those vendors. So again, more on this. So the Aviatrix controller, and now the Copilot also can deploy the firewall. It's available via the UI. It's also available via Terraform support. The controller configures the interfaces and routing entries at the firewall. This is something very interesting because we are also configuring the routing table of the firewall. There is no need to do NAT, there is no IPsec, and there is no BGP, okay? We make it very, very simple to insert the firewalls into the traffic path. Again, what's interesting is you don't have to inspect everything. You can choose which spokes and which other connections that are connected to the transit. We look at it from a transit perspective. So anything that connects to the transit can be subject to inspection. So we can, for example, let me just get my annotation running. Maybe we will go and say we want this spoke to be inspected. Maybe not this one, maybe this spoke to be inspected. Okay, so we're only doing 1 and 3, not doing 2 and 4. So you can be very selective on what traffic will be inspected. And when this happens, the transit, you can think about it like it's doing a policy-based routing, say, you know what, I received your traffic. I know it's from a CIDR range that needs to be inspected. So the transit will have to send the packet to the firewall, versus if we receive a packet that is from a VPC that does not require inspection, that traffic can go directly to its intended destination without having to be sent to the firewall. Okay, there are certain, depending on the cloud, and we'll see some differences. There are certain cloud service providers where we actually use a cloud load balancer. For example, in Azure, we always use a cloud, Azure ILB. In AWS, we have two options: one where we don't need anything, the other option where we can leverage the gateway load balancer. Both of these options are available. Again, what's nice is even when we incorporate the native cloud load balancer, we can automate the end-to-end solution, and you're not by any means supposed to go and manage that load balancer on your own. One very important point towards the end is we maintain the session stickiness. I think this is very, very important to understand. And let me try to just elaborate on this further. The problem is if this instance, for example, if an instance in this VPC, I'll mark it just with red so that, and wants to talk to another instance in the third VPC, for example, and I'm going to assume that I already decided that these two, or one of these VPCs anyways, is going to be inspected. Whenever you decide one, it means any traffic that is coming from or going to this VPC will be inspected. Okay, we always need to ensure traffic in both directions will be inspected. So the problem is as follows. When the traffic reaches, the traffic from the instance will go through the VPC router. As we have been discussing, the VPC router will send it to the spoke gateway. The spoke will send it to the transit. Now the transit has to give it to one of these two firewalls, okay? And this is done via a hashing algorithm. So the transit is gonna look at the 5-tuple and say that this particular session has to go to firewall number 1. Again, it follows a hashing algorithm. And the nice thing about the hashing algorithm is when you invert it, meaning what I'm trying to say that if the traffic flow is source is A, again, I'll try to make it simple and destination is B. Sorry, I was supposed to write. Okay, what is interesting about it is you go and invert it, meaning if the traffic comes in, it's obviously more complex than this, but I'm just trying to simplify. If the reverse traffic is coming, meaning now you're getting a reply from B and the destination is A, the hashing algorithm will ensure that we will give that particular session to the same firewall. Else, what will happen is that the request, I already drew the request, let's assume went to this firewall. Okay, this is the request. The red is the request. And now when the other instance here responds, it's a reply, right? And I am going to change my color. So the reply is in blue, else the reply might go to the other firewall. And the problem becomes these two firewalls, even though they are active, but they are not syncing state. They are not in HA from a firewall perspective. Meaning this firewall is not syncing the sessions with the other firewall. And the problem that would happen is when this firewall receives the traffic, it says, how am I seeing a SYN ACK without actually seeing the SYN? So it will reject that flow. and you'll have a problem. And this problem is basically called asymmetric traffic. So in the way the solution works is because of our hashing algorithm, you can think about our gateways acting as load balancers, where we ensure that the same flow always hits the same firewall in any direction. Okay, so this was the most important piece to understand the session stickiness and how the hashing ensures that the same firewall looks at both the request and the response, while ensuring that both firewalls are active-active. Active-active, again, means that both firewalls are receiving traffic to inspect. However, we don't mean that the firewalls are actually syncing state. Okay, so again, what we're showing here is from the spoke to transit, as we've been discussing, we always use active mesh, so you're able to actually send traffic across all of the tunnels you have. The traffic will land on the transit. What we do always is, from an availability perspective, whenever you place the transit, you place each one in an availability zone. So you're placing transit 1 in AZ-A, transit 2 in AZ-B. And this ensures that if the whole AZ were to fail, your traffic would continue to flow without interruption. Similar model we do for the firewalls. You can deploy, again, here where they're focusing on throughput and how much bandwidth, how much throughput you can get with by having 20 firewalls up to 10 in each AZ. But the logic still holds true even with one firewall and one firewall. If one firewall dies, or part of the whole AZ dies, you're still able to send traffic to the other AZ, but you can also add multiple firewalls inside each AZ for additional throughput. And again, because we can be selective on which VPCs we want to inspect, this even gives us a bit more control on inspection and controlling the firewall throughput. So the controller monitors the health of the firewalls, and I'll talk a bit on that. The session stickiness is maintained. Okay, I'll probably explain. So if there is a session and the firewall is still operational, the full session will continue to flow from the same firewall. Obviously, when the firewall goes down, then we have to distribute the sessions that were already on that working firewall to other firewalls. Yeah, so what we're seeing here is the failover. So assuming a session was coming to the transit and the transit was deciding to give it to the first firewall, if that first firewall dies, the controller monitors the management interfaces of the firewall. In addition, in AWS, the transit is actually even monitoring the interface of the firewall. So we send keep alives on our directly connected interfaces, and whenever we don't hear back the response, we would assume that the firewall is dead. Okay, so both of these methods we actually use to figure out if the firewall is alive. Anyways, when the firewall goes down, we will go and send the traffic to other firewalls that are alive. And if all of the firewalls are no longer alive, we can send the traffic to the firewalls in the other AZ. And if the whole transit is no longer alive, we can also send the traffic to the other transit and to the remaining firewalls in AZ-B. Okay, what we're really trying to prove is that from a resiliency perspective, we are able to monitor these firewalls, and we're able to react to firewall failures, and we're able to react to transit gateway failures as well as to AZ failures. Okay, so no matter what the failure is in the setup, we are able to react to it. In addition, we have alerting mechanisms. If the firewall goes down, that you can get this as a webhook or in a Slack message or even via email. There's a ton of monitoring and alerting capabilities for the FireNet solution. Okay, so what we're seeing here is the Azure deployment. As I mentioned briefly, there is a bit of difference. In Azure, we use the Azure ILB, which is the internal load balancer. In AWS, there are two options, one with or without the gateway load balancer. But in Azure, it's always the internal load balancer that is used. However, what you see, the solution is very, very similar. The traffic gets to the transit gateway. Previously, it was the transit gateway which decided to which firewall we want to send the traffic. Do we send it to the local? Local, I mean the firewall that lives in the same AZ, or do we send it to the remote firewall, which is the firewall that lives in the remote AZ? However, with the internal load balancer, we can send the traffic, we can offload this functionality to the internal load balancer. So now the transit gets the traffic. If the VNet requires inspection, we can send the traffic to the Azure ILB, and the Azure ILB always monitors the health of both of these firewalls and will decide to send the session to one of these firewalls. That is the main difference between the deployment in AWS and in Azure. Again, assuming in AWS where we are not using the gateway load balancer. The second thing I want to touch a bit on, which this slide is mainly referencing, is a single hub FireNet versus a dual hub FireNet. And that is really a common design pattern or question that many environments tend to ask is, do you centralize both east-west and north-south? So on the model on the right, we're seeing a firewall that is, the pair of firewalls is doing north-south as well as east-west traffic. So any traffic that goes to the internet goes through these firewalls. Any traffic that goes east-west goes through the same pair of firewalls. And the reason you can see that is also that the RFC 1918 as well as the default are both, from the spoke perspective, are coming to this pair of transits. So you're attracting all the RFC 1918 and all the internet-based traffic to get to the transit. Transit will give it to the load balancer, and then we will always have the same pair of firewalls. On the model, this is what is single hub FireNet. It means you are consolidating your east-west and north-south firewalls into a single pair, versus the dual hub FireNet is where you would segregate both. So on the left, you see the, you can think about it like the east-west hub or the east-west transit with its east-west firewalls. And again, this is referenced by the fact that the RFC 1918 routes will point to this transit here, to the transit that I've highlighted in blue, versus the internet-based traffic will go towards the transits that are highlighted in red. So and again, obviously, we'll hit the pair of firewalls. So here, what we've done is these firewalls are for north-south, and these firewalls are for east-west. Okay, again, it's not really an Aviatrix decision. It's more of a decision on your operations, who manages what is the blast radius, and I mean, you could argue for or against any of these design choices, but it really depends and it really varies from one organization to another, looking at factors like blast radius, like high availability, like maintenance, like upgrades, like failures. I mean, all of this, and again, a bit also on the hierarchy on, are these firewalls managed by a single team versus different teams? These are some of the questions that can help decide which model do you want to go with as an organization. Okay, so I think this is the same discussion we already talked about. You can have east-west or egress. You can have high-performance encryption we already discussed. There's no need for having IPsec or BGP or even SourceNet, which is very important. The solution is repeatable across regions and clouds. As we discussed, there are a few differences that we brought up between AWS and Azure, but what's still interesting is that the full solution is orchestrated, managed, and operated by Aviatrix. Again, to mention is we can do the bootstrapping, and actually this is something you will see in the lab, but we can actually bootstrap the firewalls to come up with an initial configuration. That is just showing that in multiple regions or in multiple cloud environments, you are able to repeat the same solutions, and you can have multiple firewalls deployed in multiple regions or in multiple cloud service providers at the transit or backbone layer. We have a capability in Azure. In AWS, we always decide if we want, so any connection that is connected to transit, we decide if we want to inspect this spoke or that spoke, for example. And this generally means is that all the CIDRs, all the subnets within that VPC will be inspected. Subnet groups is a way to get a bit more granular on what you want to inspect. So instead of looking at the whole spoke, again, this is a feature that's only available in Azure. So instead of saying I want to inspect the whole spoke, I can go and define subnet groups, which is a group of subnets. And then if that particular group needs to be inspected, this traffic will be redirected to the firewall. If not, otherwise the traffic will not be redirected to the firewall. So on the packet walk, I think I've alluded to it briefly, but I'll just walk you through it. So the in AWS, the instance always will send the packet VPC router to spoke gateway. Spoke gateway will give it to any of the transits via active mesh. The transit will, in AWS, again, remember that there is no load balancer, at least if you're not doing the gateway load balancer. You have two AZs. So this transit will have to decide, do I give it to this firewall? Do I give the session to this firewall or this firewall? Again, it doesn't matter because the hashing algorithm will ensure that even if the return traffic would go to the transit on the right, it will still give the session back to the same firewall and maintain session stickiness. Okay, so the traffic in this case goes to firewall, which is on number 4, and the firewall will do the processing, will check if it's allowed, assuming the traffic is allowed. It will go back to the transit, which is on number 3, and then which will give it to the spoke. The spoke will give it through the VPC router to the instance. And this is just the request. So there is always the return flow, which is from the 2.20 now to the 1.10 instance. So 2.20 we can give it to another spoke gateway. Again, it doesn't matter. And you can give it to this transit or this transit, doesn't matter. So in this case, we're going back to the same transit, which will give it to the firewall. The firewall will obviously do its inspection, give it back to the transit. The transit will give it to one of the spoke gateways via ECMP, and then the spoke will give it back to the original source. Okay, so what you're seeing in Azure, it's exactly the same. The only difference is in AWS, it was the transit gateway. It was this layer that had to decide, do I give the packet to this firewall or this file? In Azure, what you will see is there is a load balancer in the middle, and we will only give the packet to the load balancer, which in turn will decide to which firewall we send the packet to. So again, going back to Azure, the traffic will go to the VNet router, to the gateway. The gateway will send it to one of the transit gateways. Now, the transit gateways, as I said, does not send the packet to the firewall. It sends the packet to first, obviously, we need to decide if we require inspection. So if either VNets or in Azure, the subnet groups, we can get a bit deeper. Regardless, if any of those dictate that we need to do inspection, we will send the traffic towards the internal load balancer, which in turn will send it to, for example, in this case, to firewall number 5 on the left. And then the firewall will give it back to the transit gateway, which will continue its way, very similar now to AWS. For the return traffic, again, now this time the traffic is coming on transit, which is number 3, which is on the right. And again, the transit does not have to select anything. It offloads the packet to the load balancer. The load balancer already has an existing session, so it will send that same flow to the same firewall that we selected for the request. And then the traffic continues to flow in the same manner. So a new feature might be interesting. This is in AWS only, and it requires transit FireNets and multi-tier transit. So it's important to understand that the spokes can be anywhere in AWS or non-AWS. However, the transits, which is the two-tier the two-tier MTT architecture, I'll explain now what that means, have to be in AWS. So let me just explain it. Let's first explain the problem, okay? Assume that you have, again, this is more prevalent in a single region. When you have multiple regions, this is very common, what you're saying. But if you have a lot of spokes, hundreds or thousands, we have customers who have thousands of VPCs and spokes that are hanging off a transit, or basically that are connecting to a pair of transits. You might want to, for performance reasons, or in order to distribute the load, or even for high availability, to distribute your spokes. So assume, I'm just give an example. Again, this is not meant to be correct numbers, but assume you have, let's say 150 VPCs in total, okay? So what we're doing here is every 50 VPCs, again, these are not performance numbers to be followed in production. I'm just giving an example on what we're doing. Every 50 VPCs, 50 will have a pair of transits with firewalls. So this is what we are doing here. So this is from, for example, this is from VPC. This is from VPC 1 to VPC 50. Okay, and this is from 51 onwards. Okay, the whole idea is I'm just trying to explain till 101, and then this is, I don't know, from 102, for example, to 150. I believe this should have been, I don't know if I can find it now. This should have been probably, this should have been 100. and this should be 101 to 150, doesn't matter anyways. So the whole idea is you have multiple spokes and you're distributing a number of spokes on the transits. So if again, this is mostly the problem is here will become that we're referencing is if all of these VPCs are in a single region. And the reason I mentioned this is if you have VPCs that are globally across multiple regions, you will never try to consolidate firewalls because you don't want to send traffic from one region to another. This will affect the performance. This will affect the quality of experience for your applications, unless you're dealing with very dev or test workloads that you're okay to incur a latency hit. So generally, these are very logical requirements for the problem. So now you go to a customer and you tell them, you know what, okay, so you're having these 50, they have the transits, and then you have a pair of firewalls here, another pair of firewalls here, and a third pair of firewalls here. And this would mean that you have 6 firewalls. And generally buying 6 firewalls is not cheap. Obviously, you also need to orchestrate, to manage, to operate these firewalls, which might not be something many customers would love. So what we're doing is we are adding a new enhancement to FireNet, again, subject to the constraints that I mentioned. There is now what we call a secondary FireNet and a primary FireNet layer. You can think about the secondary FireNet as a FireNet is a transit, but it does not have a firewall. So what we're doing here, and then there is a primary FireNet which has a pair of firewalls. So the first advantage just by looking at this is we have reduced the number of firewalls from 6 till 2. By the way, this one, I mean, you don't have to have a dedicated one. It could be any of those FireNets that can be a primary FireNet. So now we have reduced the number of firewalls, which is more cost effective, and even from from a management and operations point of view. So what is happening here is a 2-level redirection problem, meaning that when the traffic reaches secondary FireNet, previously that FireNet had the firewall there, but now we don't have it. So we are going to send the traffic, like as a policy, if we require inspection, we're going to send the traffic to this transit, which will in turn give the traffic to one of these firewalls. Okay, so that is basically how it works. And again, if we are in a single region, the latency from here to here will all be very little. And we have reduced the number of firewalls from 6 to 2, and even from a management and operations perspective. Okay, so this is just the centralized FireNet model. One thing to note is you need to have MTT enabled. So what we're doing is this transit, at least for traffic that needs to be inspected, will have to be the center of the world, meaning this transit will have to have MTT enabled, okay? And will have to relay the routes between this transit, between this VPC, or even these routes and these routes. Otherwise, the transit will not have, if the transit is not going to send, is not going to do the relaying of the routes, that path will not actually exist. Okay, so that is also an important consideration in this architecture. Okay, so transit FireNets is a genius feature in my opinion, and it makes service insertion much easier. It's supported across the 4 major CSPs, and now we are going to go through a lab on how to deploy this together. Okay, so now we are coming to lab number 7, which is about FireNet. Again, I'll be walking you through it. It's pretty straightforward. So we have been dealing with the in this setup, we are going to focus on the Azure US West Transit, as this is the place where we are going to deploy our Palo Alto firewall. So we are going to deploy a firewall here. But first, if you can notice, let me just annotate, is that the line in gray here, this is Azure US West Spoke 2. We have only be dealing with Spoke 1. So first you will need to attach Spoke 2 to the transit. It already has a test VM, as everything we do. So once you attach it, next we are going to focus on bringing up this firewall. This is a lengthy lab. The reason it takes time is because the firewall takes time to be provisioned. Also, the Azure APIs can somehow be a bit slower. So overall, I just would like, we generally are patient in this one. It might take around 20 minutes for the firewall to come up. So again, let me take you through it bit by bit. Again, so the first thing is we're going to attach the Spoke 2 to the transit. So if I go to Copilot, I can go to our gateways and Spoke gateways. And there is the Azure US Spoke 2. You can see it's not connected anywhere. And I can connect it to the Azure Transit. Okay, this is going to take some time. So next we're going to focus on the firewall deployment. And what we're also doing, we are also bootstrapping the firewall. So we are already configuring the interfaces. We have the policies created, logging, the static routes. Everything is being done with Bootstrap. So let us start by let's make sure that, first of all, this Spoke gateway now is actually connected. Yes, so if you look at Azure US West Spoke 2, you can see that it's connected to the transit. If you would like to take a look also at the topology, you will be, actually did not change as of now. So I think if you give it some time for Spoke 2, you will see the link between Spoke 2 and the transit. But as long as we have it there, we are okay. Let me put the lab guide on the beginning. So now we're going to launch the firewall, and this is very, very critical because we want to make sure that we do it in the correct manner. So let's go to launch the firewall, and if we go to the controller, there's the FireNet, and we'd like to set up, and we go to the firewall. And this is where we need to launch and associate the firewall instance. We'll just give it a few seconds to do the API into Azure to get all of the details. Okay, so now the details appeared. So let's go and look at the lab guide. So we need to do the firewall instance name. So the VPC is the Azure US West Transit, as you can see. The gateway name is Azure US West Transit. This is the transit gateway's name. And this is the name of the firewall, so I'll just copy it and paste it here. Again, I will not touch anything from the bundle, the image, the size of the instance is okay. Now let's look at the IP addresses. It has to be public gateway and firewall management 1. So this one, it has to be public gateway and firewall management 1. It's important not to use the subnets that have the AZ keyword. So we just use the public firewall gateway and firewall management 1. And the next one, I believe, is the public firewall ingress egress 1. Again, does not have AZ, so that is correct. 10.0, right? And let me just verify. So it's 10.32/28 and 10.0/28. Both of them do not have the AZ. Okay. So now on username, I use AVX admin. You cannot use admin in Azure, and I'll select any password that I can remember, preferably complex password. And attach is yes, but very importantly here, before I click launch, okay, so before I click at launch, I need to go advanced because this is where the bootstrapping information is there. You will already access this from your pod info, but for the time being, I'll be copying and pasting. Again, if you're doing the lab, you will have your own information. The file share folder. Again, these are all details that will be available in your pod if you have been given access. You can think about it basically like it's basically where the Palo Alto firewall would expect to find files that it requires for bootstrapping. Okay, now that I have now that I've placed everything and all the details look to be correct, I will go and launch. I will just pause the recording as this will take time for the firewall to be up, and we'll be back in a few minutes. Okay, so we gave a few minutes for the firewall to come up, and if you go to firewall network, under list, there is the FireNet properties. There are things you can manipulate here, but what we're concerned about is getting to the firewall. You can go to the firewall tab and open this link, and you will obviously have to put the same username and password that you have set up during the configuration. Okay, so now let's go back to the lab guide. So now that the firewall is up and accessible, we still need to do one more thing, which is configuring the routing of the firewall. Okay, because we want to ensure that the firewall can route the traffic back to the transit. So what we do, we will go to what is called vendor integration, again under FireNet, and we already have the firewall. So we will edit it. and we'll say this is a Palo Alto. And if you remember, we'll have to put again the username and password, and you can save the details. After you save the details, probably you need to 1 second wait. You check just to verify that the firewall has the interfaces up. Okay, let's try it again. I believe the firewall might not have been up, so let me just do it again. I will do the same username and password, the AVX admin, and the password that I've set up. Oh, sorry, yeah, I should have selected the Palo Alto, and then I do the save. Okay, so it successfully edited the saved the information. So if you go again and now you click show, what you will notice is that the Aviatrix has configured the sorry, let me just verify. Yeah. So what has happened is the Aviatrix controller has configured the 3 routes pointing to the transit. And if we go to the static routes on the device, so if you go to network virtual routers and you look at the default routing table, you look at the static routes, you will see exactly these same routes pointing to the same transit. You will see the RFC 1918 routes programmed in the Palo Alto firewall. Okay, so this is just what we have done. Now that the firewall is up and ready, we need to decide what are the spokes what spokes do we want to inspect. Again, it's done by policy. Not everything will get inspected. It just is very granular and policy driven. So this is the transit. You will go to policy. This is transit that already has the firewall, and you will enable sorry, you will enable spoke 1 as well as spoke 2. So this is the, if you want, Azure US. So you have spoke 1 as well as spoke 2, and we will add them under the inspection policy, and we'll click update. So now what we've done is we have programmed the FireNet, specifically the transit, to send any traffic that's coming from US West Spoke 1 or US West Spoke 2 towards the transit. So the first problem that you will notice is this Azure US West 2 is not in a network domain. So it's not going to be possible to test the connectivity unless we place it within a network domain. So what we're doing here is we are editing the domain green, and we are placing Azure US West Spoke 2 within the domain green. So what I'm doing is I'm going to go to Copilot, and I'll go to network segmentation. I will go to network domains and edit the green domain. And I can place the Azure US West Spoke 2 inside the green domain. So now what we have is exactly this. So we will start SSHing into the instances. Okay, so now what I've done is I have SSHed into the instance Azure US West Spoke 1 test 1 as per the lab guide. And if you're wondering how to get their IP addresses, they will be in the portal. But again, you can always go to the topology and click on Azure US West Spoke 1 test 1 and get its public address. This is how I actually got into this machine. Let me make sure that I am sharing my full topology. Yeah. So again, so this is how you can get into the machine. And now you want to ping the, so you are here and you want to ping the Azure US West Spoke 2 test 1 as per the guide. Again, I click on it and I get its IP address. And I can ping it. Now, first of all, the ping works. And if you are to go to the firewall, you can actually see that this is the search. So this is the ping between the 192.168.1.100 and 2.100. And the ping actually goes through the firewall because we have already set the policy to inspect both of these spokes. Actually, any of these spokes would have sent the packet even to the firewall. Okay. So again, the reason this works, if you go to policy, part of the bootstrapping, you have an allow all policy, and you can see even the hits showing that this policy is being used. And this is how we can verify that even by looking at the monitor, we can verify that the traffic between these two instances is being redirected to the firewall for inspection. Now, we can also ping GCP. So if you remember, we did the ping. So from here to here, actually from this instance to the other instance, now we want to ping to GCP. So GCP, if you look at, again, you can always look at the topology. I always use that to find the IP addresses. They will be in your portal. So this is the private IP. So I'm going to try to stop this ping, and I will ping to 172.16.1.100. And I will try to see if I can also find, let me remove this filter and see, yeah, exactly. So I can see the one, and now if I put it back, by the way, it will actually work because both of them are coming from 192.168.100. So you can see the traffic that is going from Azure Spoke 1 to GCP. This is the current ping, and you can see previously the traffic that was going between the two test instances within Azure. And both of these sessions are actually going through the Palo Alto firewall that we have deployed via FireNet. Okay, so this marks the end of lab number 7 and the end of our discussion on FireNet.